right, let's talk about what we got. I think I went and talked to most of you, but I do want to have this on video for people who might go back and watch it. There is a typo. That card, if you guys go to your second page, card 6 should have been this top card 6 should be card 9. Okay. So the card 1 column was for average position of the particle over the interval. So the average value of the position. Would you guys remember which card that was? That went with card 1? 13. Yes. All right, and then card 2, the average value of the velocity of a particle over the time interval. So what's some of the ones that went with that one? Card 5. You guys already mixed up your cards. That makes it hard. 16. Yes. I don't think it's 10. 9.
Please excuse this interruption. Teachers, students who were in the second session of the ACT boot camp should be returning to 7th period at this time.
So many intercom interruptions this morning in 5th period.
Yeah. All right, so average acceleration. What do y'all think? Card 14. 11. 7 was the original one I would have picked. Anything else? 12. So those ones you've already found the antiderivative and got velocity, so the original function had to be acceleration. So I think I went around to you guys enough that y'all got that. I just wanted to put it up here for the people who didn't get to do the activity. Okay, so we're going to go through this packet, and I'm going to have packets for the next few days. This one is on, and the first part is on understanding the vocabulary. And I think these packets are written in a way for you to do them on your own, because you have these word banks, but I want to do it with you if you guys don't mind. Because I really want you to get this right, because this is highly tested on the free response. All these next packets we're doing, I can pick out 2013, the first 2 questions you need to understand what we're doing the next 3 days to do 2 questions on the free response. All right, so the first, number 1, we are going to fill in the blanks, and we're going to use the word bank only once. So to find a new position of a particle moving on the x-axis, this is kind of an old rule, but we're bringing it back. We're going to add the starting position. To the integral of the velocity. All right, so that's when, if you guys remember, we did a problem like that with the ice skater, and you knew where she was at a certain time, and then you wanted to find where she was later, and so it's that same rule. All right, and then total distance traveled we haven't done, so this is new. So if you want to find the total distance traveled, you're going to integrate the speed. So those of you who've had physics, how do you find the speed? What is it with relationship to the velocity? It's not calculus. If you know the velocity, what do you do to that to find the speed? It's one of these words, and it's not displacement. There we go. The speed is the absolute value of velocity. Speed doesn't have direction. It just has speed. There you go.
We never said that.
Oh. So what does negative velocity mean? Does it mean you're going slower? Yeah, it means you're going backwards. You're going to the left, basically, or you're going down. All right, and then number 3, to find the change in position. You're going to integrate velocity over the time interval. And then this is what displacement is. So displacement and total distance traveled are not the same thing. So displacement is going to be the difference between where you started and where you stopped. So you could have gone back and forth like 15 times, and that doesn't matter for displacement. But total distance traveled, it does matter, like how many times you went back and forth. Okay, so let's look at this graph. And we haven't found integrals graphically in a really long time. And I just assumed that my second period was really going to remember this, and I don't think they did, but they pretended like they did. So anyway, if we want to integrate graphically, so you want to find the integral when you're using a graph, what do? Do y'all remember? It was like the first thing we learned before you even knew you were finding an integral. You add and subtract areas. Good. Okay, so this graph is not labeled, but the horizontal axis is the t-axis. The vertical axis is the velocity. So this is the graph of the velocity function. All right, so part 2 says a particle moves along the x-axis so that at time t its position is given by x of t and the velocity is given by v of t. At t equals 2, the particle is located at x equals 5. The following graph gives the velocity of the particle over the time interval from 2 to 7. So that t of 2 at time 2, x is 5, that is not on this graph. This graph has nothing to do with that. This graph is the velocity. All right, so we're going to match the numerical expression to the verbal statements. So since we know we have to use areas, let's go ahead and find the areas of both these triangles. So what do you guys think about the top triangle? What's the area? 3. And the bottom? 2. Okay. All right, so if we wanted to find the total distance traveled by the particle over the interval from 2 to 7, we're going to do one of these 3 things. We're either going to add 3 and 2, we're going to do 3 minus 2, or we're going to do 5 plus 3 minus 2. What do y'all think? If we do total distance, are we going to use a negative? Right, because it's the absolute value. So what happened is this person traveled 3 whatever units, not the person, the particle, 3 units in the right direction, and then 2 units the left direction. We don't subtract those. If we want to find the total distance, we add those. I know, it's kind of tricky. All right, and then number 2, we want to find the position of the particle at t equals 7. What do y'all think? C. We have to use the original position, the starting position of 5. And then we add when we're moving to the right, we subtract when we're moving to the left. So that is going to be C. And then the change in position or the displacement that we do actually subtract. So that's going to be B. We're going to do some of these just using different representations, and I think it's going to start making more sense as we go through. I hope, anyway. All right, so for part 3, we still have a particle, and it's still moving along the x-axis. At time t, its position is given by x of t, and the velocity is given by v of t. So we have 3 expressions, and we're going to match them with the same verbal statements. All right, so we're looking for the one that represents the total distance traveled by the particle over that interval. Yes. So if you want to find total distance traveled, you integrate the speed, and the speed is the absolute value of the velocity. Okay. So don't shout it out this time, just give everybody a second. So on 2, we want to find which represents the position of the particle at time t. So look at the 2 that are left over. Which one of those do you guys think is the position A? We take the starting position, x of 2, and we add the integral to it from 2. These two match to 7. All right, and then the integral for the velocity function gives us the change in position or the displacement between times 2 and 7. All right, and then the last one, we have a tabular or a table representation of our function. And whenever you have a table to find the integral, do you guys remember what we would do with the table? The Riemann sums, right? So integrating table, we're going to use Riemann sums. And it tells you that in the problem, but I just wanted to remind you. All right, so still a particle moving along the x-axis, and its position is x to t, velocity is v of t. This time, at time t equals 2, the particle is at x equals -1. So we have this table that gives the velocity at certain times. All of these integrals are approximated using left Riemann sums. So we're going to do this matching thing one more time. So we want the total distance traveled. Okay, so on your left Riemann sum, this is one section, and this is the other rectangle if we were going to draw them. So we use the left velocity, right? So this is the velocity we would use if we were just straight up doing a Riemann sum. What would we have to multiply those by? Where did you get 3? Right, the width of the rectangle, which in this case, the difference between those is 3, and the difference between those is 2. Okay, so let's say we want to find the total distance. Would we use -4? We would use +4 because that's the absolute value one, so that's going to be B. All right, if it's asking for the position at a certain time, what do we need? What do we need though? Why? We need that initial location, the initial location of -1, which is going to be A. And then changing in position is just straight up Riemann sums using the numbers that they gave us. So that's going to be C. Okay, so this is a lot of vocabulary. Not as much like calculations, no calculations really, just vocabulary. Okay, so we're gonna have some more writing to do. Let's check for understanding. So we're gonna explain in our own words. You guys wanna use your own words? We can't, I'll listen to your words if you want to, but we wanna explain the difference between position, displacement, and total distance traveled. Okay, so when we're finding the position, we are really just finding the location of the particle on the number line. So it's just moving back and forth along the number line, and we just find a position at a certain time where it's positioned. Say position one more time. All right, and then for displacement. What are we finding when we're finding the displacement? How much has changed from the starting position to the ending position? Very good. All right, and then finally, the total distance traveled. What are we finding?
Oh, that's
I don't even know how to say that in my own words.
yeah, like displacement.
No.
Well, it's like the total amount of, okay, yeah, it's what it
This is what it is. Well, okay. If we're thinking about a particle moving left and right, it's going to be the sum of the distance left and the distance right. The distance to the left and to the right. Okay. Can the position be negative? Yes. You can be on the negative part of the number line, so yes. What about displacement? Yeah, you move. Like if you start off in the negative and you move towards the negative, you're definitely going to have a negative displacement. All right, and then total distance can never be negative. All right, so what I want you guys to do is to finish this packet. Now this is a nut strategy. Well, we'll talk about the nut strategy the next few days. So on nuts, N stands for noun, U stands for units, and T stands for time. And you can kind of see an example of what they want you to write. So the nouns are going to be like what these three words were, or possibly what we got from our cards. So these things. Those are probably going to be all the nouns that you could say. That's what you're finding today. And then units, units are going to be feet or feet per second or stuff like that. And then time could be time at one moment,